All right, what we are going to do in this section, going to look at the histogram, and while a frequency distribution is a useful tool for summarizing data and investigating the distribution of data, another tool would be histogram, which is a graph that is easier to understand and follow. A graph consisting of bars of equal width drawn adjacent to one another. That is the synopsis of what's a histogram. The horizontal scale represents classes, quantitative data, and that's important to follow. And the vertical scale represents either frequencies or percent frequencies. Important use of histogram visually displays the shape of a distribution, shows the location of a center and the spread and outliers. So here's a simple example. Again, we have seen this. Now we want to look at its histogram. So I hope you see the concept is very simple. You go with a simple grid, and along the x-axis, the horizontal axis, you can put these numbers. The way the horizontal axis works, you have three choices. You can choose to use the limits. You can use the boundaries. You can even use the midpoints. However, later on, we discuss a graph called ogive, and in that case, we have only one choice, and that is using the boundaries. And because of that, it's a good practice that we use the boundaries along the horizontal axis. So I would use the boundaries here. So you would put, for example, 99.5 here, and then 104.5, and you move on, you make up your scale. Now, on the vertical axis, you have a choice of using frequencies or percent frequencies or relative frequencies. Which one do you use? Whatever that you are asked to use. In this case, we use the frequencies. For example, if you look at the very first one, and the height, you can go, in this case, 2, 1, and so forth. So you can go from the scale, if this is 1, for example, go all the way to, I don't know, what is the largest one? 18. You can even scale it such that the largest one, I don't know, is 20. And you just pay attention to your scale. I hope everybody can come up with this simple histogram. The bars are adjacent. Look at the bottom as your horizontal axis. It contains the boundaries. And again, I'm going to repeat, you can use the boundaries, you can use the limits, you can even use the midpoints. But the best choice, boundaries. Why? Because there's a restriction for some graphs that they must use the boundaries. Therefore, it's a good choice to stick with that. Now, your vertical axis, notice, in this case, is frequency, because frequency is given. If they want us to do percent frequency, ultimately, it really looks the same. I want you to know that it doesn't make that much of a difference. Whether we use frequency or percent frequency, the shape is very similar. However, you want to be careful with your scale. So just for the sake of argument, if you pick any of these, so if you look at this one, this has number 18, and this is the height 18. So this one has the height 8. To the right of it, this has the height 13, and so on and so forth. So I hope it's clear. So coming up with the histogram, bars are adjacent. The horizontal axis uses the boundaries. Vertical axis uses frequencies in this case. Relative frequency histogram, again, as I said, it works in the same manner. Coming up with the histogram for the given, it's really not a big deal. As far as the horizontal axis is concerned, just the way it's given, you can choose to use 75 to 124 as the first one, and so on and so forth. But you can also make up your boundaries. Remember how we make up the boundaries. Look at this one. So the upper boundary for the first class is 124.5. So I'm going to write just the first class. So 75 to 124. That gives us here 124.5, which means the next class uses the same lower boundary, 124.5. The width is 50, So you can subtract 50 and you can add 50. So remember the width is 125 minus 75, which is 50. So if you add 50 to 124.5, you get 174.5. You can subtract 50 from 124.5 and you get 74.5. And this is the histogram that you have. Very straightforward. And the largest one, of course, has the frequency of 24. So this number, this corresponds to 24, 11, 10, 3, and 2. Now, relative frequency is defined as frequency divided by total size. So the relative frequency for the first class would be 11 divided by 50. The next one would be 24 divided by 50 and so on. We remember that. I think this question was done already. And remember the RF, the relative frequency, must add up to 1 or 100%. So this must add up to 100%, or we've made a mistake. The only time that it may not be 100% is due to round off error. If you have, for example, 99.9999%, or if you have 100.000, bunch of zeros and then 1%, that is acceptable. And so you graph it accordingly, and they look very similar. If you do the relative frequency or percent frequency properly, they end up giving us the same answer class. The shape is very close. Now, the thing you want to be extremely careful of when you set up your graph, this must read frequency, this must read percent. Make sure you have them accordingly. So the point being, histograms, whether we use the frequencies to make up the histogram or relative frequencies to make it up, the shape shouldn't be that much different. When we do histograms, here's what happens. We explore the data by analyzing the histogram to see what can be learned about CVDOT. C stands for the center of the data. V stands for the variation. D is for the distribution. O stands for the outliers. And T is time. And there are some common distribution shapes. Something that is bell-shaped, also known as normal distribution. A uniform distribution, the heights are the same or almost the same. Skewed to the right or positively skewed, or skewed to the left or negatively skewed. Again, those are just the shapes. I think most everybody is comfortable with this and remembers this stuff. Again, a normal distribution, it's almost bell-shaped, and we call it normal distribution. As far as skewness, a distribution that is skewed, if it's not normally symmetric, extend to one side. If it extends to one side, such as the right side is skewed to the right, or maybe skewed to the left. We are in essence repeating what we just mentioned. So if we have the histogram drawn properly, it sort of gives us the information that were mentioned here. Now what happens if the histogram is given? In this case, the histogram, when we look at the bottom, it says weights of the pointers in grams, and the top, the vertical axis is the frequency in which it occurs. So use the histogram, and we want to find the following. We want to come up with the number of subjects. The reason it says estimate the number of subjects, because sometimes it may not be easy to read from the histogram. It may be that it's close, and that's accepted. The width, boundaries, and there's a gap or what's happening with that is a normally distributed. Now, to estimate the number of subjects, it simply means add up the frequencies. So each bar has a height. You estimate the height, you add them up. So I hope everybody's clear the concept. Again, I'm going to put number 12 here for the first one. And if somebody reads it, I think everybody should read 12. But if you read, okay, maybe you think it's 11, it's not that big of a deal. I want you to know the concept is whatever that number is, look at the next one and the next one and the next one, add them up. That's how we estimate the number of subjects. What about the width? First and foremost, let's talk about the third one, the boundaries. These are the boundaries for the first class. And then these two would be the boundaries for the next class. And then you move on all the way to the end. I hope everybody is clear. So we have number one, we have number three in essence. What are the boundaries for the first one is 5.5 and 5.6. And therefore, the width is the difference between the two. When you want to calculate the width, if the boundaries are given, so the width would be upper boundaries minus the lower boundaries of the same class. Whereas in the limits, it was upper limits minus lower limits plus 1 unit. Okay, don't mix them up. Okay, so we have those. And there is a gap here. As you can see here, the height is 0 in this case. So again, can be explained. And whether it's normal or not, clearly it's not a normal distribution. Number of subjects, you need to add those heights, 12 and 20 and 8 and all the way to, then there are 80 subjects, in this case, quarters. The width, as I mentioned, 5.6 minus 5.5. And the boundaries are given for the first one. There is a gap, and that means there are two different groups, and then it's again from two different eras. The first set is 40, the second set is also 40, but two different eras. You can look them up, and clearly it's not normally distributed. Now, I want to explain one more topic that I want to go through that fairly fast. We don't dwell on it too much, and that's assessing normality. This is a piece of information, pre-1964 versus post-1964. The way it was used, 90% silver plus 10% copper, and then afterwards was copper and nickel alloy. So that's why different weights in any event. If we want to look at normality, normal quantile plot, here's what we do. Could somebody read this one for us, please?
Normal distribution, the pattern of the points in the normal quantile plot is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line pattern.
Okay, so the idea is that there seems to be a straight line if we set them up. Could somebody read this one for us?
Normal, if the normal quantile plot has either or both of these two conditions, the points do not lie reasonably close to a straight line pattern. The points show some systematic pattern that is not a straight line pattern.
Thank you so much. So this is not a normal distribution. Now, what I want to discuss is this last piece, okay, which really puts all of it together. Could somebody read this one in blue, please?
Normal quantile plot. A normal quantile plot or normal probability plot is a graph of points x, y, where each x value is from the original set of sample data, and each y value is a corresponding z-score that is expected from the standard normal distribution.
Thank you so much. So what is normal quantile plot? It has two, the pairs are as follows, x and y. Y is equal to the z, which is x minus mu over sigma. We will discuss that with more details as we look at the z-scores, and that is the normalization score, standard normal distribution, and it's coming up. But that's the idea, you plot those pairs.